Here's an introduction to Redshift to accompany Chapter 5 of the textbook Astronomy from Open Stax. So let's first take a detour to talk about the Doppler effect, because that's going to be important here for understanding Redshift, which is, just briefly, a redshift is a modification to spectrum that we observe from an astronomical object. So the Doppler effect, what this is it's a shift in the frequency of a wave due to motion between the wave source and the observer. So let's take the scenario of sound, because you're probably very familiar with this, and you're definitely familiar. You may not know it, but this happens to you all the time. So when a wave leaves a wave source, so for instance, let's say we have a speaker that we place at some location like this red dot. The waves are going to leave that source with some speed. And so for instance, we can follow one of these circles moving outward, and that would be the crest of a wave, and it's going to follow some speed. So in the case of sound, this is really like a compression wave traveling. And for sound, it would travel at the speed of sound. Okay. But if your source is moving, for instance, if your speaker is traveling, you're still going to have waves emanating from that speaker, from that source, but you're basically going to be catching up to the waves that you're chasing after, and you're going to be racing away from these waves that you're going away from them, right? And so the distance between the wave fronts in the direction that you're moving is compressed because you're chasing after those waves. The distance between the wave fronts in the opposite direction is going to be stretched because you're moving away from those waves as you travel away from it, right? So the wavelength here is increased in the direction that's opposite of the motion, and in the direction of the motion that you're moving, the wavelength is decreased. And in the perpendicular direction, nothing has changed because there's no relative motion there. And so if some observer is standing there and measuring the frequency of the waves, for instance, for the case of sound, maybe you're just sitting there with some kind of detector like your ear and listening for the beats of the wave. If your observer is standing on this side, so the direction that the object is moving towards it, then the frequency is going to be increased. If you're an observer and you're over here, away from where the object is moving, then the frequency is going to be decreased. And if instead you're standing perpendicular, you can see that the wavelength isn't changed at all. So this same effect actually occurs for light. So light is a wave, and then light is subject to the same compression and stretching due to motion, just the same as sound is. And what's important to note is that this is the motion between the observer and the source. So we can have our light source. If the light source isn't moving, there's some distance between the wavelength, and no matter where the observer is, that wavelength is the same. If instead our source is moving, so in this case the light source is moving towards the bottom of the page here, then for the observer at the bottom of the page, the wavelength is going to be compressed, right? So there's going to be a shorter wavelength. For the observer here in the opposite direction, there's more distance between the wavefronts. The wavelength is increased, so this is a stretched piece of light. And if you're perpendicular to it, the light source, there's no change whatsoever. So let's imagine now that we have a light source that is emitting green light naturally when it's at rest. If you're perpendicular to that object, then the light is still green. Let's say our light source is moving to the right, then the wavelength is going to be decreased, and so rather than being green, the light's going to be more blue. So we call that a blue shift. If you're in the opposite direction, so the light source is moving away from you, then the wavelength is going to be less green, it's going to be stretched, it's going to be longer, it's going to be more red, and we call that a red shift. Okay, so this is called a red shift or a blue shift. Generically, the phenomenon, we typically just stick with the term that it's red shifted. But blue shift, is technically accurate if the source is moving towards you. the amount that the wavelength is changed of the light is determined by the relative radial velocity between the observer and the object. What I mean by radial velocity is it's the velocity component that is along the direction between you and the source, between the observer and the source. So if an object, for instance, let's say the source, we're moving kind of diagonal, like kind of towards A, but not completely, we only care about the component of velocity towards direction A for this calculation. And so the shift in wavelength, this change in wavelength, delta lambda, this is the difference between your initial and final wavelength, this is equal to the original wavelength that you have times the velocity, the radial velocity that the object has, divided by the speed of light. So lambda is the wavelength for a stationary source. Delta lambda, this is the difference between the wavelength for a stationary source and the wavelength that's actually observed. And c is the speed of light, that's the 2.998 times 10 to the 8 meters per second. Okay, so this is an equation that we can use to determine this radial velocity. Technically, this is only true for objects that are not moving too fast, so you want to be at a few percent of the speed of light, not much more, and not too distant objects. So this works well for objects in the galaxy and nearby galaxies. Okay, so why do we care about this redshift? There are consequences for astronomy, and not just negative ones, actually quite positive consequences. So because of that relationship between the change in the wavelength and the velocity, you can do some algebra from the previous equation and see that the velocity that an object has, this radial velocity, is equal to the speed of light times the ratio between the change in the wavelength and the initial wavelength. So if we observe the wavelength shift or frequency shift equivalently, then we actually know the radial velocity of an object. We know how fast it's moving towards or away from us. And so, for instance, let's take an example here. This is an absorption spectrum. So the sun is, not really moving radially from us. We move a little bit towards and away from it, but not very much. So this is pretty much fixed. You can take a look at a distant galaxy, and you see this absorption pattern here looks the same, but is shifted in the red direction. And so you could pick any one of these lines and see how much that wavelength has changed, and that gives you this change in wavelength, this delta lambda. And we can use that to determine the velocity. So the redshift itself is referring to the ratio between the change in the wavelength and the original wavelength of the spectral line if the object were not moving relative to us. So let's just take an example. So let's say we have some spectral line. It could be absorption, it could be emission, it doesn't matter. A spectral line that's normally at 400 nanometers. And yet we observe it at 410 nanometers, so a bit longer. So then the question we would pose is, how fast is this object moving away from us? So we can calculate that. We know that from the equation above, the velocity is equal to the speed of light times the change in wavelength divided by the wavelength for a stationary object. So we plug in our value for the speed of light. Here we calculate the wavelength difference. So now it's 410 nanometers. It was 400 nanometers. And we need to divide this by the wavelength that it would be for a stationary object. So we can do that, and 410 minus 400 is known to its friends as 10. We can then divide 10 by 400, that's 0.025. And we see that our velocity that this object is moving is 2.5% of the speed of light, which you can calculate that in terms of a velocity with units of meters per second. It's about 7.5 million meters per second, or 7.5 megameters per second, so pretty fast. But that's the kind of thing you can do, and that we do all the time, to actually take advantage of redshift to determine the motion of very distant astronomical objects. This is important because these objects are so far away, you'd never physically see them move. If you just put your telescope and looked at it, and had your telescope look at it for your entire lifetime, most of these objects you'd never see any physical shift, but you can use this tool of redshift to determine how fast it's actually moving. So, just as a word of caution here, is this the object's total velocity? No, not necessarily, right? This is just the velocity along the direction of motion between us, the observer, and the object. So this is the radial velocity. So it could be moving very fast perpendicularly to our direction, and we wouldn't see that from this tool of the Doppler shift. So, we can use this Doppler shift then to determine the motion of stars. So let's take an example here. The spectral lines for the sun, we're just looking somewhere in the infrared. You see is the green lines here. And then let's instead look at the star Arcturus, and you see that everything shifted a little bit to slightly longer wavelength. And so we now know Arcturus is moving away from us, and we could calculate that velocity based on the small wavelength difference here. And so, for instance, we can do this with something like the Big Dipper, a constellation that you're probably all familiar with, and we can see that actually, that constellation shape for an observer from Earth changes over time. So it didn't used to be a dipper. If you look now, you kind of have something that looks like a ladle or a dipper. If you go 150,000 years from now, it's completely smashed beyond all recognition, and that's because the stars that make up that constellation are moving. And if for some reason you have 3D glasses in your home, you can use that here, and you'll get a three-dimensional image. That's why you see all points mirrored in red and cyan. So sorry, I can't provide those to you, but if you have them, this is a fun image to look at. Okay, another interesting consequence of this Doppler shift in spectral lines is we can determine the rotation of stars, which is pretty wild if you think about it. If you're looking at this very distant object, a star to us from Earth just looks like a point of light. How would you see that that's rotating? This is one tool to do that. So when the star is rotating, part of the atmosphere is going to be moving towards an observer and part is going to be moving away. So just imagine for a moment spinning a basketball on your fingertip, right? One part is moving towards you and one part is moving away. And so it's the same thing with a star. Pretty much every star is rotating with some rotational speed. And so, that means that one part, the part that's rotating towards you, is going to be blue shifted because this object's moving towards you, or this part is. The part of the star that's rotating away from you is going to be red shifted. And then there's a continuum along the surface of the star, and of course along the axis of rotation there's no shift whatsoever. But we can't just choose to view one part of the star, like the left of it or the right. These are very distant objects. You're just getting the light from the whole thing all at once. And so when you observe a star, you see the red shifted part and the blue shifted part and the non-shifted part all at the same time. Okay? And so that means that's going to broaden your spectral line, and the width of this broadening is going to be related to the rotation rate. So if we have a spectral line at some wavelength, that can be red shifted, can be blue shifted, and so the spectral line itself is going to be very broad, and as you see in this plot here, you can use the width of that line to actually determine what the surface velocity is of this star. And if you have an estimate of the radius, then you can determine the actual rotation rate of the star. And then there's another consequence for astronomy building on top of that rotational line broadening. So for the past, I guess, 20 years, but 10 years really in earnest, the field of studying exoplanets has taken off in astronomy. And so we can look at planets on distant stars, and we can figure out that they're there and determine some of their properties. And one way that we can determine that these planets are there and determine properties of their orbits is by looking at how spectral lines are modified. So specifically what happens is you have a planet orbiting a distant star, and it's going to block some of the star's light if it passes between us and the star. So for instance, this is a real case. This object is we believe passing in front of a star here. right? So the star itself is rotating. In this case, the left part is towards us, blue shifted. The right part is rotating away, it's red shifted. And this planet's going to block, one part or another depending on where it is in its orbit. And so it might temporarily block part that's blue shifted or that's red shifted. So then we can look at our spectral line, and this is actually inverted here, and you'll see a ripple going through it if you look carefully. The vertical line is indicating where to look for the ripple, and that's because you're either blocking some of the blue shifted light or some of the red shifted light. And you have this broadened line from rotation, and you block part of it, and so believe it or not, you can analyze this ripple and determine where this object must be passing in front of the star, and you can learn some things about its size and all of that business. It's kind of incredible. Now, one complication, and it's not a huge complication, due to the Doppler shift, is spectrum interpretation, right? So when we want to know the composition of an astronomical object, we can look at, for instance, the absorption spectrum to determine what the atmosphere of that star is made of, because the different absorption lines, as you know, corresponds to different atoms or molecules being present in the atmosphere of that star, as an example. But it's not enough to look for a single line at a known wavelength that we've measured on Earth. These can be redshifted because of this Doppler motion. And so we actually need to observe a pattern. We need to look for a pattern like the one you see here. We try to do a pattern matching to see the pattern has shifted, and then we know specifically which line we're looking at, and we can calculate redshift. Now, I want to clarify before I close this lecture out that the Doppler redshift is only one type of redshift, right? So the Doppler shift is literally due to motion between us, the observer, and the astronomical object. But there are other types of redshift that we'll talk about later in the course, and you'll hear discussed generally in astronomy, and I want to distinguish between those. So there's one called a cosmological redshift. So as we'll cover in the future, the universe is constantly expanding. So everything is moving away from us, essentially, when you look at the bigger scales. And so that means, space is literally physically stretching. And any light wave that's traveling through that space is expanding. It's getting stretched too. It's expanding the wavelength. And so what that means is we can actually use the redshift as a measure of the distance, because a photon that was produced a long time ago, for instance, in the Big Bang, it's going to be continually stretched as the universe expands. It's traveling at the speed of light, and so time and distance here are directly related. And so the amount of redshift that we see, that tells us how far away it is, right? Because space has been expanding that entire time, and this is known as the cosmological redshift, and this is how we measure the distance to objects that are very far away, so distant galaxies, for instance. Just want to note, for a close by object like a star within our galaxy or even nearby galaxies, this effect is tiny and we don't really worry about it. The Doppler redshift that we've discussed earlier is much more significant. And for completeness, there's another type of redshift that is not due to actual relative motion between us and the object. It's not due to space expanding. It's another one that's known as gravitational redshift or surface gravitational redshift. And this has to do with general relativity, which is quite complicated, and so let's just talk about it in simple terms here. So there's something known as the equivalence principle from Albert Einstein. This is a concept that acceleration due to gravity and physical acceleration are equivalent from a physics perspective. So if you take Physics 2001, for instance, you'll see this to some extent, that we can use the equations of motion and equations of gravity in a sort of interchangeable sense. So gravitational acceleration and physical acceleration are the same essentially from a physics perspective. Okay. So now if you think about that, then that means if you're near, if a photon is emitted near an object with a really strong gravitational pull, so something like a neutron star that weighs as much as the sun but is the size of a city, there's a very strong surface gravity there. And so light is experiencing acceleration towards the massive object that it is escaping. Okay, so even though the photon is escaping, it's leaving that, it is experiencing acceleration towards the object. And so that is going to stretch the wavelength of light out. So that light is going to be redshifted. And so this isn't accurate here. This is more of a cartoon. But for instance, if we have this object here and a blue photon were emitted, you have a very strong redshift and it becomes a red photon in this cartoonist picture. And that's another type of redshift that we care about, but in this case, really only for very dense massive objects. And that is it for this introduction to redshift for Astronomy 1000.